Okay, so like an articulation point, so an articulation point again is with regard to a vertex. So we were doing finding whether a vertex is an articulation point or not. Now something similar to an articulation point, we can have what is called a bridge edge for an edge. So this is now for an edge. Okay, so we want to decide whether an edge in a graph is what is called a bridge edge or not. So again, the definition of a bridge edge is similar to what we call the definition of articulation point. So if you remove that edge, if the graph is going to get disconnected, then that edge is called a bridge edge. So let's see an example here. If I remove this edge, say 0, 3 from this graph, then you could see the graph is going to get disconnected, because when I remove 0, 3, you're going to have a component of vertices just involving 3 and 4 and another involving just 0, 1 and 2. Similarly, if I remove this edge 3, 4, the graph is going to get disconnected because 4 is going to get isolated. We are going to have 0, 1, 2, 3 now together. So on the other hand, if I remove, say, this edge 0, 2, the graph is not going to get disconnected because because if you remove an edge, the vertices are still going to be there. So all the vertices 0, 1, 2, 3, 4, all the 5 vertices are going to still stay connected. Similarly, if I remove this edge 1, 2, the 5 vertices are still going to stay connected. Similarly, 0, 1, if I remove it, the 5 vertices are still going to stay connected. So in this graph, 0, 3 and 3, 4 are the bridge edges, because if you remove either of them, the graph is going to get disconnected. The other 3 edges are not bridge edges. Now we could again, like a brute force approach, manually go through, remove each edge and run depth first search and see whether the graph is going to get disconnected or not. But that's like a very time consuming process. So again, we can make use of the result of depth first search when you run it just once and make use of that result, analyze like how we did for an articulation point, the 3 edges and back edges, and you should be able to decide whether an edge is a bridge edge or not. So that's what we're going to do now. So let's look at the general the rule, and then we come back to this graph and apply that rule. So we want to decide whether an edge, say UV, is a bridge edge or not. Okay. Now again, you are going to do this analysis after you run depth first search and identify the edges as 3 edges and back edges. So that means you have a depth first search tree, and then you have a root node for that tree, and then based on the root node, you should be able to locate which of these two vertices U and V is closer to the root node, right? So most likely, let us say, it's easy for ease of visualization, the root node is somewhere here on the top, so you are coming further down from the root node, so U is, say, relatively closer to the root node compared to V. So basically we need to identify that thing. So which vertex is relatively closer to the root node of the depth first search tree? So the vertex that is closer to the root can be called the upstream node, and the vertex that is further away from the root, in this case V, can be called, say, the downstream node. So now what we need to look at is look at the subtree associated with the downstream node, in this case, which is V. So there's the subtree, because you see now this edge, so there's a rule that like leaf node is not an articulation point, back edges are not articulation point. So we are going to look at only the tree edges and decide whether the tree edge is a bridge edge or not. So UV, first of all, should be a tree edge. So if UV is a tree edge, there should be a subtree starting from V. Now you check whether from that subtree is there at least one back edge that should go to either U or some vertex above U in the depth first search tree. Now you see the rule is kind of a little different from articulation point. The case of articulation point, if you go back and look at the rule, what I said is from each of these subtrees there should be at least one back edge that goes above u. So if you have at least one back edge from each of the subtrees attached to u, then u is not an articulation point. And if there is at least one back edge, if there is at least one subtree from which there is no back edge that goes above u, even if there is a back edge, it goes only up to u, right? So if there is at least one subtree like that from which there is no back edge that goes above u, then u is an articulation point. So there should not be any back edge that goes above u. All back edges can go only up to u from that at least one subtree in order for u to be called an articulation point. Now for a bridge edge, in order to call edge as a bridge edge, now you have identified this downstream vertex v and the subtree involving this v. Now if there is at least one back edge that goes even to u, then uv is not a bridge edge. So it means even if there's a back edge, all back edges should be within this subtree v. No back edge should go out of that subtree and go to either u or above u. So that's the difference. In the case of articulation point, the back edge from that subtree could go up to that vertex u. Still u could be called an articulation point. So there the back edge should not go above u. So here the back edge should not even go to u. The back edges, if at all they are there, should start and end within that subtree. If there is at least one back edge that goes out of the subtree to either u or to any vertex above u, then that edge uv is not a bridge edge. Again, it's a simple reason, because logically you'd see if I remove this edge uv through this back edge that goes from the subtree to u, the vertices in the subtree can still reach the other vertices in the graph. So the graph will stay connected. So only if a back edge, if all the back edges start and end within the subtree and no back edge goes out of the subtree, then if you remove this edge uv, the vertices in the subtree are going to get disconnected from the rest of the vertices in the graph. So that's the reason why we say that even if there's a back edge that goes just to u, then uv is not a bridge edge. So in the case of articulation point, the rule is little different. There could be back edges that go up to that vertex. No back edge should go above the vertex in order for the vertex to be called an articulation point. Whereas here, in order for the edge uv to be called a bridge edge, there should not be any back edge that goes even up to u. If there's at least one such back edge that goes up to u, then uv is not a bridge edge. So let us apply the rule here. So you run depth first search, say starting from 0, and this is the depth first search tree you get. So you draw the tree edges and back edges. So this is the only back edge between 0 and 2. So now let us look at this edge 0, 1. So if you look at this edge 0, 1, 0 itself is the root, so that's the upstream node, so 1 is the downstream node. So that means you're looking at the subtree involving 1 and 2. So from the subtree involving 1 and 2, you see you have a back edge between say 2 and 0. So this back edge goes actually above 1. So the rule is from that subtree of the downstream node, if there's a back edge that goes either to this 1, which is the upstream node, or above the upstream node, then this edge 0, 1 is not an articulation point. So here you see here from the subtree there's a back edge that goes to 0. So 0, 1 is not an articulation point. Sorry, 0, 1 is not a bridge edge, because it's a back edge that goes up to that vertex 0. Similarly, 1, 2 is not a bridge edge, because now for the edge 1, 2, 1 is the upstream node because it's closer to the root, and 2 is the downstream node. So again, from that subtree there's a back edge that goes actually above 1. So because of that, 1, 2 is not a bridge edge. So you can actually remove that edge and see if the graph gets disconnected. In this case, not. So that way you can cross check whether you decided it right or wrong. Now look at the edge 0, 3. Now again 0 is the upstream node, 3 is the downstream node, so you're looking at a subtree involving 3 and 4. Now there's no back edge from the subtree that goes up to 0 or above 0. So because of that 0, 3 is a bridge edge. So if you remove the edge, graph is going to get disconnected. Similarly 3, 4, 3 is the upstream node that is closer to the root node, 4 is the downstream node. Now again the subtree involving just 4, there is no back edge that goes either to 3 or above 3. So because of that 3, 4 is a bridge edge. So again going back to for the bridge edge, so if we say 0, 1 is a bridge edge, is a bridge edge or not, we want to decide. So 0 is the upstream node, 1 is the downstream node. So from the subtree involving 1 and 2, there is a back edge that goes up to 0. So because of that 0, 1 is not a bridge edge. So in each case you need to tell as part of an answer because of what reason you call this edge as a bridge edge or not. So if the edge is not a bridge edge, then you have to tell me because of what back edge the edge is not a bridge edge. Okay, now let us go through one more example. So this was the first graph that we started depth first search. So after running depth first search, this is the depth first search tree. So again you can always refer to this slide in order to decide. So let us look at this edge 1, 2. Now 1 is the upstream node because 1 is the root node, so that's closer to itself. Now from this subtree involving 2 means everything starting from 2, that's one subtree. So for this is a subtree involving 2, 4, 3, 5, 6, 7. You have 2 back edges. One back edge between 7 and 1 that goes up to 1, and one back edge say between 3 and 1 that goes up to 1. So the rule is either the back edge should go to the upstream node or even above is okay. So in that case that vertex 1, 2 is not a bridge edge. So in the case of 1, 2, because of 3, 1 and 1, 7, the 2 back edges, it's not a bridge edge. Now let us look at this edge 2, 4. So 2 is the upstream node because it's relatively closer to 1, the root node. So 4 is the downstream node. Now from this subtree starting with 4, then we have 3, 5, 6. You have 3 back edges totally, but 2 of them start from 5. One of them starts from 5 and ends at 4. So this back edge basically starts and ends within the subtree. Similarly, this back edge starting from 6 and going to 4 is also starting and ending within the subtree. Now, but there's one back edge starting from 3 that goes above 2 from that subtree. So from this subtree involving 4, 3, 5, 6, there is at least one back edge that goes out of that subtree and goes to vertex either to 2 or above 2. So in this case above 2. So because of that reason, because of this back edge 3, 1, the edge 2, 4 is not a bridge edge. Okay, so that's the way you have to identify whether edge is bridge edge or not. So in the case of say 2, 7, so again you have 2 is the upstream node, 7 is the downstream node. Now from this subtree involving just 7, there is a back edge that goes above 2. So either the back edge should go up to 2 or above 2 in order for the edge to be not a bridge edge. So in this case the back edge goes above 2. So you can say 2, 7 is not a bridge edge because of 7, 1. Now similarly let us look at 4, 3. 4 is the upstream node because it's close to the root, 3 is the downstream node. Now from this subtree you have 3 back edges actually. So one back edge starts from 5 that goes up to 4. Now because of this back edge itself, we can say this 4, 3 is not a bridge edge because there's one back edge that goes up to 4. Now even this back edge starting from 6 that goes up to 4, will make this edge not a bridge edge. Similarly, this back edge between 3 and 1 goes actually above 4. So all these three edges, 6, 4, 5, 4, and then 3, 1. So, or actually any of one of these back edges is sufficient to rule out this edge 4, 3 from being not a bridge edge. But so now we have 3 back edges, because of which 4, 3 is not a bridge edge. So similarly for each edge, so even like case of 3, 5, and this one subtree now starting from 5 and 6, so you have 5, 4 goes above 3, then 6, 4 also goes above 3. So you have two back edges that go above 3. So because of this 3, 5 is not a bridge edge. Now for 5, 6 again you have one back edge that goes above 5. So because of this back edge 6, 4, 5, 6 is not a bridge edge. So as part of your answer, you should do like this. So draw the depth first search tree with the tree edges and back edges, and for each of the candidate edges. So why I say candidate edges? So remember, the back edges cannot be a bridge edge. So they automatically get ruled out from being called a bridge edge. So the only candidate edges we have to look at are the tree edges. So write down all the tree edges, and for each tree edge, again you identify the upstream node and downstream node. Look at the subtree involving the downstream node. If there is a back edge that goes either just to the upstream node or above the upstream node, then that edge is not a bridge edge. If there's no back edge, or if all the back edges start and end within that subtree, then that edge can be called a bridge edge. Okay. So now, like if a graph is connected and there's no articulation point, we call the graph as a biconnected graph. Now similarly, if a graph is connected but there are no bridge edges, then the graph is said to be two-edge connected. So something similar to vertex. So in the case of the bridge edges, if there's no bridge edge in the graph, when the graph is connected, then we can call the graph also as a two-edge connected graph. Okay, it's just the terminology you have to remember. Alright, so any question? Let me save this video.